Hi, today we're doing notes for 5.5, multiple angle identities. And in this section in your book, there are actually several sets of multiple type identities. It talks about double angle identities, it talks about power reducing formulas, and it talks about half angle identities. Of those different types in this section, we are really today just going to focus on the double angle identities, which are these identities right here. You find them on your Trig help sheet, the purple sheet on the bottom back here, and you have your sine 2 theta. You have 3 different ones for cosine 2 theta that you could use. It kind of depends on what you're doing in the problem. Like if you have this in the problem and there is no sine in the problem, then you wouldn't use this one because it does have sine in the identity, and you wouldn't use this one because it has sine in the identity. So you'd be using this identity. So you kind of have to look and see what you have and what you're trying to work with to help decide which ones of these you're going to use. And then there's a tangent of 2 theta, which is this identity right here. There is another alternative to tangent theta that I'm going to work with today too, and that's this last one right here. It's not listed on your purple help sheet, so if you want to add that to it, feel free to do that. This one I pop up and use if it's a problem where I've already calculated 2 theta or 2x, and I've already calculated cosine of 2x. Since I already have those two values, I can jump to this one instead of going and calculating it here. This one does tend to produce more fractions, so it's just kind of another way to avoid a little bit of that. Over here is just a little bitty blurb kind of reminding you of the very first day we did multiple angles was on solving trig equations, day 1, where we listed out like 3 theta equals, and we listed all the angles, and then we divided everything by 3. So first we solved for ku, k being a constant, and then we divided by k to get our results. So that's just kind of a reminder of what we did with multiple identities on that first day. We are going to work through these 7 examples today in our notes and practice a lot of different things. So like here is an all solutions without restrictions, so we'd have an equation. Here's rewriting. Here's given cosine of x, find these different things with different kinds of multiple angles. Here's another solving, but this time it has a restriction. Here's one where we actually have to draw in our triangle in a certain area and then calculate, and this is another just pure solving with a multiple angle. So there's a variety of problems here that we're going to work through. So let's talk about problem 1. On problem 1, this is solving 2 cosine x plus sine squared x equals 1. It is all angles, no restrictions, so that tells us that we need an equation for an answer. And so we're going to use the identity. So here's 2 sine x. So I'm going to replace that with 2, 2 sine x cosine x. And then I'm looking at what I have once I replace it, and I have something here, a plus sign, something here, so I can factor out the greatest common factor. So notice there's a 2 here and a 2 here. There's a cosine x here and a cosine x. So I can divide out my 2 cosine x, and I'm left with 1 here. And I'm left with the sine x from over here. So now I have 2 factors. Remember, the goal is not to throw a bunch of fractions in here and give us all these reciprocal or quotient identities and fractions, because when I'm solving, I want factors, not fractions. Okay, so once I have my factors, then I set this factor to 0. So I need to know what angles have a cosine value of 0, and those happen at pi over 2 and 3 pi over 2. Remember, when you're doing this diagram, your angles should be labeled. If I see a little x with a dot here and a dot here and nothing else, I will not be giving you any credit for that graph, so pay attention to that. The second factor, I move the 1 over and I have a negative 1, and so that's happening right here at 3 pi over 2. So you have to kind of be a little observant, because the first equation, this is halfway around a rotation in the circle. So we know that we can go halfway and get back here and halfway and get back here. So we know that's bouncing back and forth. So that tells me I just need to write one equation for all the solutions on the factor of cosine x equals 0. But also notice that there's a 3 pi over 2 here and a 3 pi over 2 here. So I don't need to write an equation for this one, because this angle would already be represented in the first solution, set. So when I write my equation, I'm only going to have one angle to use. So I'm going to say x equals, because it is a solution. Then it would be pi over 2, because that's my small angle. Then I'm going to rotate it halfway around the circle, so I add in pi, and then I have my nes to make sure that rotation stays in whole numbers. So this is what your answer for number 1 would look like. Problem 2, rewriting using double angle identities and graph on the interval 0 to 2 pi for y equals 4 cosine squared x minus 2. So this one is going through techniques of solving with double angles, but it's also giving you a chance to review your graphing skills. So as we work through the steps, the first thing I should notice when I have this equation is they have a common factor of 2, right? This is 2 times 2, this is 2, so I factor out the 2. I'm left with 2 cosine squared x minus 1. So if I look at my identity sheet, 2 cosine squared x minus 1 is right here and part of the group of angles that represent cosine 2 theta. So I'm going to take this and replace it with cosine 2 theta. So now I have something that is graphable. We know transformation-wise this a value in front is a vertical stretch by 2. We know that this 2 inside is a horizontal compression by 1/2. So I know that that changed my period on my graph. So first thing I would kind of do is keep track of that period. So originally cosine has a period of 2 pi. So I would take 2 pi and divide it by that b value right there. So I know that my period is pi, my amplitude is 2 because it's had that vertical stretch. So it's going to go up 2 and down 2. Period of pi means the whole V-shaped graph will occur by the time I reach the value of pi on my horizontal axis. And so by the time I reach 2 pi, I will have a second V that's going to be graphed at that point. So I went ahead and used my transformation table and multiplied all of my x's by 1/2, multiplied all my y's by 2. So we have all of these angles here and their corresponding values. Some of you are really good at transformations and you may be able to just list the transformations, but you will either have to say vertical stretch by 2, horizontal compression by 1/2 and do the graph, or do a transformation table and do the graph. So you do have to have some backup to what and how and why you're graphing. So this is what my graph is going to look like, or does look like, I guess, not going to. Here are my transformations. So if you were going to do the transformation route because you're pretty good and you can label all of these points without needing the table, then you would have this and you would have all of these values labeled, not just every once in a while, but every value labeled and your values here labeled. And then my points go from 2 down at pi over 4, I'm at 0. At pi over 2, I'm down here at -2. At 3 pi over 4, I'm here. At pi, I'm right here. And so that's one period. And we need to always graph 2. So then we'll start here and graph the second period. And you can see by the time I get to the 2 pi, there are 2 cosine waves that have been graphed. So it's been horizontally compressed. Otherwise, it would have ended with 1 V when it got there. And now it ends with 2. All right, so that is question 2. Question 3, given cosine of theta equals 5/13 from 3 pi over 2 to 2 pi, so that's a restriction. It's just an inequality notation instead of interval notation. We're going to find these values, sine of 2 theta, cosine of 2 theta, sine of 2 theta, and sine of 4 theta. And we'll talk about how to get that one here in just a minute. So the first one that we're doing is, or first thing we need to do is lay out our triangle so that we have the values out of our triangle to work with this problem. So the first thing I do is graph it correctly. So I need to graph a triangle where cosine is positive. Cosine is positive in the first and fourth quadrant, but it's restricting it right here to go from 3 pi over 2 to 2 pi. So it has to be in this quadrant. And so once I do that, I can lay in my cosine values of 5 and 13, and I can use Pythagorean theorem to find the length of the missing side. So I need my triangle complete before I begin anything. So the first thing we're doing is sine of 2 theta. So sine of 2 theta only has one identity. That's 2 sine theta cosine theta. Let me try that again, guys. Sorry. 2 sine theta cosine theta. All right, so then I'm going to go into my triangle. I'm going to get these values of sine and cosine, and I'm actually going to crunch the numbers to find the value of sine of 2 theta. So I have 2, and then sine of theta out of my triangle is -12/3, and cosine out of my triangle is 5/13. So you multiply the tops, you multiply the bottoms, and you get the fraction -120/169. So that's the first one we're calculating. Now we're going to calculate cosine of 2 theta. So cosine of 2 theta, you got to kind of pick what you want to use. I used 2 cosine squared theta minus 1 because that had the least amount of substitutions. that I was going to make, and I'm already working in cosine, so it made sense to use the cosine version. So I'm going to go to my triangle and get cosine of theta. I'm going to square it, multiply it by 2, and then subtract 1. So that problem looks something like this. So we have 2 from this problem. We have 5/13 is the cosine value in the triangle. So I'm going to square it, and then I'm going to subtract 1. So I know at this point, once I get this cleaned up, I'm going to have to get a common denominator with that. So when I said 5 times 5 is 25, 13 times 13 is 169, I know because 169 times 1 is 169 that my common denominator needs to be 169. So I rewrote the whole number 1 as a fraction of 169 over 169. That way I had my common denominators when I got down to this step. So I multiplied 2 times 25 and got 50, 1 times 169 and got 169, and now I can subtract 50 minus 169 and get my value of cosine 2 theta, which is negative 119 over 169. So on the next one, we're calculating tangent 2 theta. And this is the one I'm going to use that alternative form because we've already calculated sine of 2 theta earlier in the problem, and we've already calculated cosine of 2 theta just now in the problem. So if I use this version, I don't have to go back and do anything else. I can just work with the numbers I already have. If I hadn't calculated 2 theta or cosine of 2 theta, then I probably would have just used the standard tangent of 2 theta one that's here on your help sheet. Okay? Alrighty, so now that means I'm taking the value I got here and I'm dividing it by the value I got there. So a little more fraction work. And we know that whenever we divide two fractions, we multiply by the reciprocal. So when I have the reciprocal here, I can see 169 is going to eliminate with 169 because anything divided by itself is what? That leaves me a negative times a negative, 120 times 1, and 1 times 119. So my answer is 120 over 119. So that gets me through to that. Now I'm going to start talking about how do we figure this out for a multiple angle that's 4 theta. It's not one of the direct identities. So we'll kind of talk about how to adjust for that. Okay, so first let's think about what this means. If I have sine of 4 theta, that's saying I have sine, and really that's just 2 times 2 theta. So I always think about this as kind of doing one of those u substitutions we talked about. In other words, I'm going to replace 2 theta with a u so I can figure this out, and then I'll plug the 2 theta back in the end. So if I use my identity, sine of 2u equals 2 sine u cosine u. Now remember I said my u was 2 theta, so everywhere there's a u, I'm going to replace it with 2 theta, 2 theta, 2 theta. So what I have here is 2 times 2u, or theta, 2 times 2 theta, which is 4 theta. Here I have 2 sine 2 theta cosine 2 theta. And that's the identity that I can use for sine of 4 theta. So if I wanted to find sine of 6 theta, then I would think 6 theta equals sine times 2 times 3 theta, right? Because 2 times 3 is 6. So I'm going to let my u be this piece right here, which is 3 theta. And remember my original identity on our help sheet is 2 sine u equals 2 sine u cosine u. And then wherever there's a u, I can plug in this substitution that I have right here of 3 theta. So I have a 3 theta here, here, and here. So on this side, I have 2 times 3, which is 6. So there's my 6 theta. And on this side, I would have 2 sine 3 theta cosine 3 theta. So that's how you adjust when you have multiple angles bigger than 2. Okay? So we are going to do and use that adjustment for sine of 4 theta. So remember, sine of 4 theta over here was 2 sine 2 theta cosine 2 theta. So that's the identity that I'm using with this 2 sine theta. So that's what we came up with. So I've already calculated sine of 2 theta and cosine of 2 theta. So I can already use those values. So I have 2, which is 2 over 1, sine of 2 theta, which is 120 over 169, and cosine of 2 theta, which is negative 119 over 169. So when I multiply the tops and the bottoms together, I'm going to get a negative, and I'm going to get an extremely large value. So can you imagine how much bigger this would get if we were doing sine of 6 theta? This number would get really, really big. All right, so then that takes care of sine of 4 theta. Number 4, solving sine of 2 theta sine x. Solving sine of 2x sine x equals cosine x. I threw an extra symbol in there. Sorry about that. On the interval 0 to 2 pi. So we do have restricted answers here. So we're going to have to manipulate or work with this. Okay, so here's what I'm working with, and here's what I'm solving. And I know that I have an identity right here from my help sheet, so I can make that replacement. So I get rid of the multiple angle. I have it down to, notice, single cosines and sines along the way. I know that when I solve anything, it needs to be set to 0, so I'm going to move that cosine over here so that it's set to 0. And now I need to start using my factoring skills, because remember, that's what I need is factors to be able to set to 0 to be able to solve. So I can see that I have a cosine here and a cosine here. So I'm going to take the GCF out, and when I take out the cosine here and the cosine here, I'm left with 2 sine x times sine x, which is sine squared x, and I have the 1 right here. So it's okay that you have two different trig functions because they're in different factors. So we're going to take this and set it equal to 0. We're going to take this and set it equal to 0. So over here, 0 only happens, cosine is only 0 at pi over 2 and 3 pi over 2. So I'm going to get some solutions from here. And then on this side, when I take 2 sine squared x minus 1 equals 0, move the 1 over, divide by 2, take the square root of both sides, remembering to put my plus or minus, then I can either think of it as 1 root 2 or I can think of it as root 2 over 2. And we should know that that root 2 over 2 means we're dealing with a 45 degree or pi over 4 angle. And since it's plus or minus, there are 2 places where it would be positive, 2 places where it would be negative. So we're looking for a pi over 4 angle in every quadrant. Now, it says from 0 to 2 pi, and these are within 1 rotation. All of these are within 1 rotation. So then you want to think, how many solutions do I have? And in fact, on this one, you have 6. You have the 2 angles from here and the 4 angles from here. So your solution set would look something like that. On number 5, it says rewrite 4 minus 8 sine squared x using double angle identities. So when I'm looking at this, I notice the 4 and the 8. That means they have a common factor of 4, which I'm going to pull out. And that leaves me with 1 from this term. And when I take 8 and divide it by 4, I get 2, and I still have the sine squared theta. So then at this point, I have a double angle identity right here. It's one of the 3 that you can use for co2 theta. And so since that's it, then I'm going to replace it with cosine 2x in our case, because we're using x for our angle. So my answer is for cosine 2x. So that was pretty short and to the point. On number 6, we're given secant of u equals -5/2. We're given the restriction to be from pi over 2 to pi. And we're going to find sine of 2u, cosine of 2u, and tangent of 2u. So the first thing we need to do, remember, is to draw the triangle, filling in the missing sides if there are any, and then make sure we get it drawn in that restriction. So pi over 2 to pi over 2 to pi means you're in quadrant 2. So that's where we draw the triangle. And the right angle is back here, again, never at the origin. And then we fill in from -5 over 2, and we have the negative here because the hypotenuse is never negative. We use Pythagorean theorem to find the length of the missing side, which is square root of 21. So now that I have this done, then I can begin to address and answer those questions. So the first one is sine of 2u. So sine of 2u, I'm going to use 2 sine u, cosine u. Notice it was a u here, so it's a u here and here. Always be consistent with your notation. Then we go up and get the sine value out of here, the cosine value out of here, and multiply it by 2. So sine is 21, square root of 21 over 5. Cosine is -2/5. Don't forget to multiply it by the 2 right here. So I'm multiplying everything in the top, everything in the bottom, and I get 4 root 21 over 25. And so that's 2u. So now we're going to do cosine 2u. So this is the identity that I picked. You can't just always use the same identity all the time. You have to use what you need, but in this case I have a little more control over which version of it I want to use, so this is the one I picked. Alright, so I go up to my triangle and I get cosine of u, or in this case cosine, oh my labels did not match up. Sorry about that, guys. That should definitely be a u. So when we are doing this one, we're going to square the u, and then we are going to multiply by 2 and subtract 1, so I'm going to need some common denominator here. So cosine in the triangle is negative 2/5. Negative 2/5 squared is positive 4/25. We're multiplying that by 2, and we're getting a common denominator of 25 because when I multiply 1 by 25, I get 25, so I just rewrite 1 as 25 over 25. So then what I'm trying to do is 8 over 25 minus 25 over 25, which leaves me with negative 17/25. Okay? So that's how you would do 2u. So this time when I do 2u, I'm going to go ahead and use the identity that we have on our paper just so you can see how that one works. And then on the other side of the page, I did work it like we've been doing so you can see them side by side. So tangent of 2u equals 2 tan u over 1 minus tan squared u. So obviously the first thing you need to do is go back to that triangle and figure out what tan u is, because that's what you're going to need for the identity. So out of my triangle for this problem, tangent is negative root 21 over 2. So then I have to plug that in. So I have some fractions within fractions going on, so you just have to be diligent and patient. And so down here we need to square this, so we need to take square root of 21 times square root of 21, which is 21. 2 times 2 is 4. A negative times negative is a positive. So on top, this is multiplication, remember, so those 2's would cancel and you're left with negative root 21. On the bottom you have 1 minus, because this would be plus once you square it, 21 over 4. So then we need to get a common denominator down here. So 1 becomes 4 over 4, and we have 4 minus 21 over 4 on the bottom. So on the bottom I now have negative 17/4. Well, we know when we divide by a fraction, we multiply by its reciprocal. So we take the negative 21 over 1, which is in the numerator, times 4 over 17, and remember it's negative when I'm multiplying. So a negative times a negative is going to give me a positive answer, and my final answer would be 4 root 21 over 17. So that's how I would handle using that identity. So you have to see, you do have to be a little careful with the fractions because this can easily going to be set up to be a fraction within a fraction. Since we already had sine of 2u and cosine of 2u, we could do it like we've been doing, where I took the value of this divided by the value of this, and then when I use the reciprocal, because when you divide by a fraction you multiply by the reciprocal, the 25's cancel and you're left with the same thing, 4 root 21 over 17. Just a little shorter, more direct rate to get there. So it's important, if you're going to use this identity, be sure you state your identity you're using. If you're going to use this one, be sure you state the one that you're using. And that would take care of tangent. And finally, problem number 7. Again, have a list of angles. So the first thing we're going to do is get into the habit of adjusting our domain, because we're solving for 3x, not just x. So we didn't do that before because we were going to build into it today. But remember, this is the original domain for sine of 3x equals 0. And we want to solve for 3x. So that means, remember, a 3 right here is a horizontal compression by 1/3. So that means we're going to adjust our domain to reflect that. So I'm not solving for x, I'm actually solving for 3x. So what do I do to x? To get to 3x, I multiply it by 3. And if I multiply this part by 3, I have to multiply this part by 3, and I have to multiply this part by 3. So I get my new restriction. Once I have my restriction, then I'm going to build my problem. Solutions from 0 to 6 pi. So just like we do on any other given problem, we are going to make a graph. We're going to show the rotation from 0 all the way around to 2 pi. Remember, up here in the original restriction, it's less than, so that means that you are not including 2 pi. So you're really only looking from 0 to 2 pi. Okay, so you can't use 2 pi. So I set it up like we did in day 1, 3x equals, and then one rotation around is 0 and pi. That means you're going from 0 to 2 pi. The second rotation, so we have our first rotation we just talked about from 0 to pi. The second rotation then is you're just going to add 2 pi, and now we have 2 pi and 3 pi. And then we remember we got to go all the way up to 6 pi, so we need to do one more rotation that's going to get us out to 6 pi. And so if you come back to the rotation before, add 2 pi, I get 4 pi and 5 pi. And so we just list all of those angles out all the way through to the 6 pi. Once we do that, then it's just like we did in day 1. We're multiplying everything through by 3, or dividing everything through by 3, or multiplying everything through by 1/3. And so now we actually have our final answers. All of these answers would be required on the test. So you can see there's 6 possible solutions for this problem. All right, that kind of wraps up those 7 problems we talked about at the beginning. Different things that we could be doing with multiple angles and specifically double angle identities. Thanks, guys.